Yeah, okay, right now you're welcome back to Integrated This is Mathematics. So today I'm gonna teach you how to find out a region under how to find out the area of a region using limits. Right. Sometimes someone can say we're gonna find out the integral using limits. Right. So that also can be defined. But I hope to introduce you few more separated video series for differentiation and integration geometrically, right? So at this moment, let me pick a very primitive, very ordinary function. Right, okay, this is f of x equals to y equals to x squared. This is a function, right? So as you hope, I'm gonna find out the area of the region from little a to b. Let's assume that this is what I want to find out. This shaded region, right? Okay. So at this moment, I'm not gonna use the integration directly. This is pretty much equal to integration, but without using integration axioms directly. It means really integration is formed with a combination of summation and limits, right? Okay. You can see there are let's imagine there is a very small, very tiny, pretty much small, small and small slide, right? So if you can imagine it, it will be decreased up to a rectangle, right? Up to a rectangle. So this particular width is delta x, right? Okay. So then you can see there is a graduation. There are sort of graduations. These are with these b minus a. If you need to manage 5 rectangles, but it will not be look like rectangles because you need to divide it up to infinite number of, sorry, you don't see it, little b minus a, because you're not able to say those are that is made of rectangles, because we need to make it an infinite number of we need to see the infinite number of rectangles, otherwise we're not able to say because of this curvature, right? Okay, so now we could an idea here. F of x I is the codomain, right? Is the codomain times f of xi. This is right. Okay, times delta x. This is the width, pretty much smaller and smaller width. So height times width will be giving you the area of this pretty much a small region, rectangle, right? So we need to get the summation from here to here. It means if height starts from first one, right? It starts from first graduation, and then you can find out what about the height here. F of x1, right? F of x1. So now he will be looking for this width. So that is pretty much easy to be calculated, b minus a. I'm going to divide it into infinite number of graduations. So then only you can find out this pretty much a small width, right? Okay. So this times I, because height, it will give you the, sorry, this is the domain. So which graduation you need to find out which height you need to find out, then you need to assign here little I, right? Let me do it. B minus A upon A, right? After this one, this is all right. Here also, obviously, right? Sorry, B minus A upon N times 2, because you need to add 2 times to find out the codomain, because the codomain will be changed after this function, right? Okay. And also you need to let I goes to, sorry, from first graduation to end graduation, let n approach to infinity, right? Okay, I'm gonna manage it here. So this is the expression what you need to apply. According to this function, you can see this should be B minus A upon N times I squared. So then only you can find out what about the corresponding codomains or heights of their rectangles, each of their rectangles. What about the width? Each of their width, same subdivisions, how we need to manage B minus A upon N, right? If you are given something different where ranges, you can manage it up to your range, right? I have picked from little a to little b. So this number of slides should be managed from first one to end one. Let an approach to infinity. It means we are gonna make it a pretty much small slide, right? Okay. Let me show you how this calculation can be done. I'm really sorry about this. I'm gonna clean this one, right? Right. Okay. Because I don't have the space here. Right. Somehow we know B minus A upon N cube is a constant. B minus A upon, this is N cube, this is cube, this can be taken out, but there is a limit, so we need to keep keep 1 upon N cube inside of this limit, right? Limit and approach to infinity. Once it's simplified, it will be look like N cube. This is the summation I squared from first one to nth one, right? Okay. B minus A cube. Limit and approach to infinity 1 upon N cube. This is what we know with summation. This is a well-known thing, so I'm not gonna prove it once again, right? N times 2 n plus 1 times 2n plus 1 upon 6, right? Okay, so there is a discontinuous point, you can take it out. Once you simplify it, 1 plus 1 upon n times 2 plus 1 upon n upon 6 n cube. These discontinuous points will be cancelled out together. B minus A cube. So then you can see final resultant is, final resultant would be B minus A cube. This is 3 upon 6. Sorry, this is 2. So 1/3 times B minus A cube, right? Once you integrate from little a to little b, the same answer can be derived. It means we have found out the area of this region, of this given region under this particular curve could be evaluated using limits and summation only. We have not used here integration, right? Okay. Using the same way, you can manage each of your functions. What you need to find out the particular region, the area of particular region, if you have something issue with any function, it could be sometimes a transcendental function or exponential function, yeah, someone else. If you have something issue with arranging them properly, you can put a comment, right? Okay, so hope you could have an idea about this. Okay, thanks for watching.